Hi guys, I hope that you are doing very well. In this chapter, we're going to be switching gears a little bit. We're no longer going to be talking about equilibrium in focus, although we will touch on equilibrium toward the end of the chapter. But in this chapter, we're going to be covering chemical thermodynamics. And to put it in context, first of all, chemical thermodynamics studies how heat and work participate in chemical reactions and physical changes. And again, to put it in context, basically in chapter 4, you guys learned about chemical reactions, things like combustion reactions or precipitation reactions or neutralization reactions. Then in chapter 5 of the new book or chapter 3 of the previous book, you learned about stoichiometry, which basically is in what proportions do substances react and in what proportions do they form products. Then in chapter 14, we talked about chemical kinetics, about how fast the reactions were occurring. In chapter 15, we introduced the concept of equilibrium and the equilibrium constants, which basically tell you to what extent does one of these reactions occur, how much of it actually goes toward the product side, or what is the equilibrium between the reactants and the products under any given set of conditions. Now in chapter 18, where we focus on thermodynamics, we're going to be looking at the energetics of these processes and the spontaneity with which these reactions are going to occur. Speaking of spontaneous reactions, a spontaneous reaction is one that occurs without outside intervention under indicated conditions, whether quickly or slowly. Now I want to focus on three things here. First thing is, again, that a spontaneous reaction occurs without outside intervention, right? That's what makes it spontaneous. The next thing is, notice that I say under the indicated conditions. That means that a certain reaction or a certain process can be spontaneous at one set of conditions, let's say at one temperature and pressure setting. But if you go and you change those settings, then it is probable that that reaction will no longer be spontaneous. It really depends on the conditions, and we'll talk about examples of that in a little bit. And now the last thing that I wanted to focus on here is that a spontaneous reaction can occur quickly, or it could occur also slowly. We'll talk about examples of that as well. Now, spontaneous reactions are one directional. That means that if a spontaneous reaction occurs in one direction, the opposite direction will be not spontaneous under the same set of conditions. Again, if I change the conditions, then that could change. Examples of spontaneous reactions are shown here on the right-hand side. I mean, we all know that if we take a set of eggs and we drop them onto the floor, what's going to happen spontaneously is that they are going to break. What would not be spontaneous would be for those eggs to come back and reform into the nicely shaped eggs anymore, right? On the right-hand side, we have another example. Let's say that I have a gas in chamber A, which is separated from chamber B through a valve. Chamber B is evacuated, which means that there is no gas on that side. What would be spontaneous if I open the valve is for the gas in A to flow toward chamber B, which was empty initially, until we have the same amount of gas on both chambers. That would occur without outside intervention, without me actually having to pump the gas or something like that. Now, what would not be spontaneous would be if I had this set of conditions right now here, and for me to expect for the gas in B to flow back toward A by itself. That process would not be spontaneous. Now, I could make it happen if I change the conditions on my chambers, but of course that would be a different a different scenario. All right, examples of spontaneous processes are shown here. Things like a ball rolls down a hill, a gas fills a container uniformly, which is actually what we had in the example in the previous slide. Heat flows always from a hot object to a cooler one. Now here, at a temperature below 0 degrees Celsius, we know that it is spontaneous for water to freeze. And we know that at a temperature above 0 degrees Celsius, we know that it is spontaneous for ice to melt into liquid water. Notice here that we have the same substance, but under a different set of conditions. Negative temperatures versus positive temperatures in degrees Celsius for water. And you can see that different processes are spontaneous at those two different conditions. All right, most spontaneous processes are actually exothermic, but not all. So I want you guys to remember this, that most of the times they are exothermic. A spontaneous process will be exothermic, but not all the times. And we're actually going to be talking about what scenarios would determine whether a reaction is spontaneous or not, other than just the enthalpy or the exothermic character of that reaction. So I do want you to remember that not all the times would this be true. Okay, so a couple of questions. What variables can affect the spontaneity of a process? And one of the things that you guys already know that would affect it would be the temperature. For example, the example that we just discussed about water, right? At different temperatures, different processes would be spontaneous. For example, it would not be spontaneous for water to evaporate at a temperature of less than 100 degrees Celsius, but it would be spontaneous for water to evaporate at a temperature above 100 degrees Celsius. The other condition or other variable that affects spontaneity would be pressure. Pressure as well can affect whether a reaction is spontaneous or not. Now, are spontaneous processes always fast? And the answer is actually no, absolutely no. Some processes are spontaneous, things like burning, but however, there are other processes that are very slow or could be slow, things like corrosion of a boat over time, or the chemical reactions associated with the formation of stalactites and stalagmites in caves, right? Those chemical reactions could take a very, very long time to occur. So definitely spontaneous things do not need to be fast, but they could be fast. All right, and one thing that I forgot is that one of the driving forces to making a reaction spontaneous is going to be entropy, and that is what I want to introduce right now. So entropy could be viewed as a measure of randomness, a measure of disorder, or a measure of spread. And I tend to use the word disorder. So in your head, I want you to think about molecules that could be like really nicely organized versus molecules that now have like a lot of motion and are moving all over and are mixing with one another and have no order. So that change in terms of an increase in disorder is typically what's going to drive a reaction to occur. Now, entropy is described by the letter S, capital S, and the units that we're going to be working with are going to be mostly joules per mole Kelvin. Notice that both the mole and the degree Kelvin are on the bottom, on the denominator. This dot is just indicating that these two are multiplied by one another. Now notice that this is in joules, so we're going to find that in most of the tables in joules, but in some problems we might have to change it to kilojoules. Remember that 1 kilojoule is equal to 1,000 joules. Now, entropy increases when there are more energetically equivalent ways to arrange components in a system. All right, so let's break that down. The entropy increases, or the disorder increases, when there are more equivalent ways to arrange components in a system. So what I'm talking about here is imagine that you have one group of molecules, and that group has just 5 little molecules, versus you have one group that has 6.022 times 10 to the 23 molecules. How many arrangements do you think that you could have in one versus the other? Basically, in one, you could have 5 different arrangements, at least. In the other one, you could have 6.022 times 10 to the 23 arrangements. So the more molecules that you have, the more disorder that you have, the more the entropy that you have. And here we're going to be talking about these kind of arrangements or number of arrangements that we could have. They are termed microstates. So how many microstates could our molecules be in? Which the more microstates you have, the more arrangement possibilities that you have, the higher the entropy, the higher the disorder. Now those microstates are symbolized by the letter capital W, and we can use this equation actually to calculate the entropy by taking K, which is the Boltzmann constant, which is given right here, times the natural log of W, where W is those microstates. Now this equation, we're not really going to use it in this chapter, but I wanted you to see it just for you to see the relationship. The more possible arrangements that you could have of your molecules, the greater the entropy. All right, So let's take a look at the factors that contribute to increasing the entropy of a system. One of those is going to be the phase of that material. What I'm talking about here is whether your molecules are in the gas state versus the liquid state versus a solid. And as we can see here, there's a lot more order on the right than on the left. Remember that a gas is made out of molecules that are far away from one another and molecules that have high kinetic energy and are able to move along within the container, right? They have total freedom to move around past one another, bounce against the wall, etc., etc. So they're continuously moving. There's a lot of disorder here. Versus in a liquid, the molecules are much closer together, yet at this point they still have enough kinetic energy to be able to slide past one another. And that's what makes a liquid be pourable. That's why a liquid can flow, because the molecules can still pass one another. On the other hand, as we go to the right, we continue increasing the level of order. Here we have an amorphous solid. Amorphous means that the molecules are molecules or atoms are all next to one another in a certain configuration, but that configuration is not order. So amorphous means that there's no order to that arrangement. Think about it like all of the molecules or all of the atoms were just suddenly frozen in whatever place they were. But being a solid, all of those atoms or molecules are next to one another. And being a solid, you also don't have enough kinetic energy for those atoms or molecules to be able to pass one another. So because of that, the solid doesn't really move, right? But there's no significant order. They're all kind of just frozen in state. And then on the right-hand side, we have a crystalline solid, which is kind of the highest level of order that you could have. So in a crystalline order, all of the atoms are arranged in a perfect configuration, basically in a pattern that continues over and over throughout that crystal. That would be the highest level of order that we could have. So now if we think about entropy, the one on the left, the gas, is going to be the greatest entropy. And as we go to the right-hand side, we're going to be decreasing in entropy because to the left, we increase in disorder, increase in entropy. To the right, we increase in order, which is the opposite, or I should say it the opposite. I should say we decrease the disorder, and therefore we have the lowest entropy. Now, I wanted to go ahead and tell you guys to take a look at figure 18.1. It actually has a nice video that shows you the actual molecules moving in a gas versus in a liquid versus in a solid. So you can again see kind of the level of entropy among these different phases. One other thing that I wanted to mention while in this slide is that because the gas phase has the highest entropy of any state, any reaction that produces more gas particles than it started with is likely to have a high increase in entropy. What that means is that, let's say that I'm starting with a chemical reaction that has liquids and solids, and my products are a gas. Well, a liquid and a solid, just because of their arrangement, they're going to have a lower entropy. So if I form a gas, then that means that I am increasing the entropy significantly. Similarly, let's say that I have a chemical reaction that has both a solid and a gas as a reactant. If my product has more moles of gas than my reactant, then I'm basically converting the solid reactant into a gas. And so that means that I'm still gaining significant amount of entropy. So I want you guys to kind of think about this here, and we're actually going to have an example that touches on this just to make sure that you guys see that connection. Anytime that you're forming more gas out of any solid or liquid, that gives you an increase in the entropy level. All right. The next factor that contributes to entropy is going to be temperature. As we know, when we increase the temperature, we are also increasing the kinetic energy, right? Increase in temperature is equal to an increase in the kinetic energy. Kinetic energy is the energy of motion. Oops, energy kinetic energy is the energy of motion. So if we increase the temperature, we're basically allowing the molecules to have more movement. And the more the molecules move, the more disorder that we're going to have, the more randomness, the more spread. And so the entropy for higher temperatures is going to be greater than the entropy of lower temperatures. The next factor that is going to contribute is going to be the number of moles during a reaction. If you have more moles, you're going to have more microstates. You're going to have more possibilities of arrangements of molecules. And so what that means is that if you have more moles, the entropy is going to be greater than if you have less moles in a particular system. All right, now because entropy is an extensive property, what that means is that the entropy increases as the amount of substance involved in a process increases. All right, and by amount of substance, I mean not just moles, it could be grams, it could be the liters of substance, right? So the amount of stuff that you have is going to affect the entropy, is going to increase the entropy. At the same time, if you're just looking at, let's say, one molecule of one compound versus one molecule of another compound, the number of atoms, as the number of atoms increases in a molecule, so does the entropy. For example, let's say that I'm looking at H2O versus H2O2, and I'm just looking at one molecule of water, one molecule of hydrogen peroxide. Well, hydrogen peroxide, by virtue of having two oxygens, so one extra atom, that would make it have a higher entropy than this one right here, than the water. The reason for that is that any molecule, even in the solid state, has the capability of moving in at least the vibration states, meaning that even water would be able to kind of stretch the bonds, stretch the distance in between the atoms that are covalently bonded. At the same time, the angle in between the bonds can actually change just momentarily. And you could also have this kind of thing happening. Now, molecules that are in the liquid and in the gas state also have the capability of rotating, as is shown here on the right-hand side. So the more atoms that you have, the more of these possible arrangements that you could have. If we have one more oxygen attached to this molecule, then we could have one more possible state in which the atoms, let's say, are closer to one another or farther away from one another. There's just more possibilities of arrangement. So if you have more atoms in a molecule, that is also going to increase the level of entropy. All right, the next factor is that the entropy tends to increase as the ions of a solid crystal are solvated. So let's look at the example here. We have a sodium chloride crystal that is surrounded by water, right? It was just placed in the water. If we compare the entropy of this solid crystal of sodium chloride in the solid state as shown here versus, once it has already been solvated here on the right-hand side, the entropy has increased as we go to the right-hand side because now there's less order for that particular compound. Now I put an asterisk here and I said in general. And the reason for this is that in certain cases, the dissolution process can actually decrease the entropy because it might force the water molecules or the solvent molecules to arrange in a particular manner and lose disorder. So the dissolution process might actually end up in a decrease in disorder compared to what is shown here. So this is not true in all cases, and that's why I put kind of there a disclaimer, but it is true in most cases, and at least most of the cases that you guys will be exposed to at this level. All right, so let's look at an example. For each of the following, select the system that has the greatest entropy. And number 1 says we have 1 mole of hydrogen gas versus 3 moles of hydrogen gas. 1 moles versus 3 moles of hydrogen gas. So what I'm hoping here is that you guys realize that we said that the amount of matter, the amount of stuff that you have actually matters, right? The higher the amount of matter that you have, the higher the entropy. And so because of that, the 3 moles of hydrogen gas are going to have greater entropy than 1 mole of hydrogen gas. And before I move on, I just want to make sure here that as we're thinking about this, when we're asked for greater entropy, that also means that we're looking for greater disorder, greater randomness, greater spread of stuff. All right, let's look at number 2. So water in the solid state versus water in the liquid state. All right, so which of the two is going to have greater level of disorder? Well, the water in the liquid state, right? Because in the solid state, the molecules are not just close together, but they're also no longer able to move or slide past one another. While in the liquid water, even though the molecules are close together, they have enough energy to be able to move past one another. And so the number of microstates, the number of possible arrangements of those molecules are significantly larger. Number 3, we have iodide in the gas state versus iodide in the solid state. In this case, the entropy of the gaseous iodine is going to be much, much higher than that of the solid state because of the fact that now the gas molecules are not just able to move significantly more, but they're also significantly farther away from one another. They have a significant more freedom. And so that means that there's significant more disorder, significantly more number of arrangements for these particular gas molecules. Number 4, we have 1 mole of oxygen gas versus 1 mole of ozone gas. Notice that the only difference is that we have O2 versus O3. So in this particular case, what I was hoping is that you would actually identify that the ozone was going to be the one with the higher entropy, higher level of disorder. And the reason for that is that this one has 1 extra atom in that molecule, which means that there could be more possible arrangements or more possible microstates for the ozone versus the oxygen gas. And the last one, 1 mole of hydrochloric acid gas, 1 mole of hydrogen chloride in the gaseous state versus 1 mole of argon in the gas state. In this case, I was hoping that you would use kind of the same train of thought here to identify that the HCl would be the one because of the fact that it has 2 atoms versus only 1 atom in the molecule. All right. Before I move on, I just wanted to mention that there's an example and a practice problem that I recommend that you guys do that is on a similar kind of train of thought, basically enabling you to be able to predict which system can be more spontaneous, which system has the greatest entropy based on just the conditions. All right, continue with the same idea. In this case, what we want to do is that we want to look at the sign of the delta S. We want to say if it's negative or positive, if it's going to be less than 0 or greater than 0. And of course, greater than 0 indicates an increase in entropy, which means an increase in the level of disorder. So what we're going to do is that we're going to look at specific chemical processes or chemical reactions, and looking at what's happening in that reaction, we're going to decide whether the disorder is increasing or decreasing. If the disorder is increasing, that means that we are gaining entropy. That means that the change in entropy is greater than 0. So let's go ahead and begin. First example, what we have is silver chloride in the solid state, which is dissociating or dissolving into silver ions and chloride ions. All right, so what I'm hoping is that you were able to identify the fact that we took a substance that was a solid, so something that was very organized, and now we have dissolved it into a solution where now the ions are mobile, they are in solution, they are occupying a greater volume, they are also in a liquid state now, and so they have completely increased in disorder. So the disorder increased. Now, what happens to the delta S? If the disorder increased, that means that I gained entropy. The level of entropy for that system has increased. So that means that delta S is going to be greater than 0 which means it's going to be positive. All right, number 2, what we have is hydrogen gas and oxygen gas reacting to form liquid water. In this particular case, we are taking gaseous molecules that had a lot of freedom, a lot of disorder, and now we turn them into a liquid molecule. By changing that phase to a liquid, we are now restricting the volume that these molecules can be in to a much smaller volume because the density is significantly higher in a liquid. And so we have lost a lot of freedom. We have lost a lot of disorder. So the disorder is going to decrease. And if the disorder decreases, that means that I have lost entropy. That means that the change in the entropy is going to be less than 0, or the change in the entropy is going to be negative. Finally, in this case, we're taking 4 iron molecules, or sorry, 4 iron atoms as solid, and we're reacting them with 3 molecules of oxygen gas in order to form iron 3 oxide. And iron 3 oxide is a solid. So notice that we have solid in both left and right hand side, but we also had a reactant that was a gas. That means that overall what we ended up doing was taking a gas and forming it into a solid. So what that means is that now we have restricted the mobility of those oxygens significantly, and we have decreased the level of disorder. So we're going to say that we have decreased the disorder, and that also means that my delta S is again going to be less than 0 or negative. All right, question for you guys. Which of the following processes is going to result in a decrease in the entropy of the system? Please give it a try, and as you're doing so, notice that I'm asking for a decrease in the level of entropy. Decrease in the entropy. All right, pause your video. All right, so if you are looking for a decrease in the level of entropy, that means that we're looking for a decrease in the disorder. That's the way that I like to think about it. And so we were looking for a process in which we maybe took a gas and turned it into a liquid or a solid, or a process in which we decrease the number of moles of gases, or let's see, what else can I think of? A process in which we decrease the temperature, right? So let's take a look. A is taking oxygen as a gas at a low temperature, and we increase the temperature. Whenever we increase the temperature, we increase the kinetic energy, we increase the mobility, we increase the disorder. So this one was noted. B, we have nitrogen gas at 25 degrees Celsius, and we turn that into nitrogen as an aqueous solution at 25 degrees Celsius. We are now restricting the gas that was very, very free and occupying a large space, into now being an aqueous solution. In this case, we have decreased the disorder for sure. This was our answer. Again, we're taking a gas. The gas has the highest mobility, the highest freedom, the highest number of possible arrangements. And now we're turning it into a liquid by solubilizing that nitrogen into a solution, an aqueous solution. So that was our answer. Let's take a look at the rest. In this case, we have solid water, and we're turning it into liquid water. So we are basically taking a solid, melting it into liquid water. That going from a solid to a liquid, that increases the disorder. So that was not it, of course. The next one, we're taking ammonia as a liquid at a negative 34.5 degrees Celsius. We're changing it into a gas. Going from a liquid to a gas, we are significantly increasing the level of disorder. So that was not it. The next one, we have water as a gas, turning into hydrogen gas and oxygen gas. All of them are gases, so the change in phase is not, there's no change in phase, so we cannot use that as a train of thought. What we have to look at in this case is going to be the number of moles. We started with 2 moles of gas, we ended with 3 moles of gas, so therefore we increase the number of disorder, because the more molecules we have, the more levels of arrangements or possible arrangements that we could have, the more disorder that you could have. And for that, you can also think about, assume that you are taking care of kids. It would be a lot less disorder if you had one kid versus if you had 10 kids. That would be crazy. Lots of entropy. Next one, let's say that we have water as a solid, and this one is actually sublimating into water as a gas. And so in this particular case, what is happening is that we are increasing the level of disorder a lot, a lot. So that was not it. And then the last one, we have sodium chloride as a solid, and that one is decomposing into solid sodium and chlorine as a gas. So the solid, there's no way to compare this, but taking a solid and forming a gas, doesn't matter how much of gas we're making, just the fact that we have formation of a gas, that right there tells us that we are increasing the disorder significantly, and that's the reason why this one was not the case. This one right here, I want you guys to pay special attention to. This is the comment that I had put a couple of slides before, where I said that whenever you are doing a chemical reaction that ends up in the formation of a gas or more moles of gas, that right there means that you are increasing the entropy for that system. So in summary for entropy, a positive delta S of the system results when there is a phase change from solid to liquid, there is a phase change from solid or liquid to gas, the dissolution of a solid into an aqueous solution with an asterisk because this is not always the case, an increase in temperature within a phase, meaning that we just have a single phase, let's say a liquid, and that liquid increased temperature. And finally, an increase in the number of particles, and that could be the increase in the number of moles, the number of molecules, the number of atoms within a molecule.